Hey, Mr. William, what are you doing?
Hey, I found a secret.
Ah.
We're gonna get rich.
Okay. Can you share with me the secret first?
Can.
Oh.
Look at this. What is this?
It looks like gold chloride, gold 3 chloride.
Gold 3 chloride. Alright, and here I have potassium iodide.
Okay, and then?
Remember last week in class, we learned that when Ecell is more than 0, the reaction is spontaneous.
Okay.
Okay, so let's look at the E0 value of gold 3 plus to gold. What's the E0 value?
Oh, so the gold 3 plus become gold solid. Oh, that's how you get rich. It's 1.50, right? And you got to add in your iodide. The E0 value here is 0.54. So if I calculate the E cell, it ends up with a positive number. So that means that we can actually get gold. We can get rich.
Yes, come let's do it. Let's wait.
So Mr. William, what are you going to do when you get rich?
Oh, I tell you, I have a dream, I always wanted to be Aladdin.
Oh, okay.
And I wanted to be Prince Ali and go to Agrabah to find my Princess Jasmine in a magic carpet.
Okay, weird dream, but okay. But then what happens to me?
You? How about you be my genie?
A few moments later.
It doesn't seem to be doing a reaction yet.
Okay, then we continue waiting lah. We just continue waiting.
We'll just leave this aside, okay? Maybe we continue with the lesson first. We'll come back to this in a short while, okay?
Can. So last week we were looking at this very important idea of E cell. If it's positive, it is going to be a spontaneous reaction. And of course, we understood that this cannot be done only just for a electrochemical cell. Now, it turns out for any kind of redox reactions, right, you can actually use E cell to predict the spontaneity of the reaction. So it turns out, once again, positive means that it's going to be spontaneous, and if it's negative, it's going to be non-spontaneous. Okay, so this was something that we saw under this particular column over here. But the idea of spontaneity, we learned from a few chapters ago from last year, J1, right? We have this same concept that tests spontaneity. What kind of concept is this, Mr. William?
So it is delta G when we learn in energetics.
Right. But delta G is a bit weird, right? Because for spontaneous reaction, it is going to be negative. It will be an opposite sign. If it's non-spontaneous, it will be positive. But if it's spontaneous, it will be negative. So it turns out there is a opposite relationship between my E cell and delta G. And this is going to be clearly reflected inside this new equation that you must learn. Delta G equals to negative NF E cell. Okay, so a couple of things you must note. Number one, the units. You tell me that delta G, the units is going to be in joules per mole. Okay, it's a bit different from normal. We usually do kilojoules, but in this case, it's going to be joules. Your E cell is going to be in terms of volts, right? And F is going to be a constant. What constant is this?
Faraday's constant.
And what's that value?
96,500.
Okay, so this is going to be found in the data booklet. Okay, now what is going to be a bit weird over here is this N over here, right? So we're going to use an example to illustrate how do we find this N. So Mr. William, would you run us through the work example at the bottom?
Yep, sure. All right, so I think the portion on N is the one that students generally get a bit confused about, right? So what we have to do is we think about balancing the equation, right? As we know, there's always going to be a reduction equation, there's always going to be an oxidation equation. So before we combine the equations together, we have to ensure that the electrons loss equals to electrons gain.
That's right.
Right? So when we learn redox, we will say we have to manipulate this to make sure that they have the same. So what you can do is to multiply this by 2 and to multiply this by 10. Right? So as you balance the whole thing together, you will notice there are 10 electrons on the left and 10 electrons on the right. We usually don't write it, but in this case it's important because it makes us realize that there are 10 electrons that's being transferred in this particular redox reaction. And that's what the N stands for, the number of electrons that's involved in the overall equation.
Okay. So in the event that if I go and times 2 to the equation, that means that when I do the calculation, it must be 20 electrons, right? So in other words, I can think of it as the N is going to be the lowest common multiple of the electrons in the half equations.
That's right.
Okay, too much of the talking already. I want to see whether I get gold or not. Can you show me?
Yes, that's more important, right?
Correct,
okay, let's check this out.
It looks the same.
Nothing, right?
Okay.
Maybe just need a little while more.
Oh, okay. Let's wait. Okay.
A few minutes later. 3 days later.
Low.
10 years later.
So much later that the old narrator got tired of waiting and they had to hire a new one.
One eternity later.
It didn't work, Mr. William.
Yeah.
Kids, don't try this at home. It doesn't work. So, Mr. William, can you give me maybe 3 reasons why this didn't work?
We thought that it's spontaneous, right?
Yes, correct.
So technically spontaneous should work.
Yes.
I should be in Agrabah right now.
Correct.
You
I should be a genie
right now.
Yes.
But it didn't.
Yes.
So there are 3 reasons
okay.
why Ecell is positive but the reaction may not work.
Okay, so maybe I go through the first one.
Yes, sure.
So I think this reaction, so long already, still haven't happened, this must be a very slow reaction. So delta G did not consider the kinetic factor, right? It could be that the activation energy is way too high. So the reaction is way too slow to be even observed. So at the end of the day, despite having a delta G that's negative, the reaction may not happen. That's reason 1.
Yes, right. Now, the second reason why the reaction didn't take place could be the conditions that we subject to. Right? So for the reaction to work, we have to really subject them to static conditions, which is 1 mole per dm cube, 1 bar, and also
298 Kelvin.
298 Kelvin, right? But our conditions may not be exactly that. So you can see, right, when things are not under static conditions, any sort of changes, temperature, pressure, concentration, it may affect the values.
Sure. The last one is probably because there may be a side reaction. I think just now when you're talking, you spit some saliva inside. So I think it's a side reaction going on. Maybe it prevented my gold tree to become gold. So I think that's your fault.
Maybe got COVID.
I think so. So yeah. So some other side reactions may have occurred. Okay. Okay, our gold experiment didn't work. So one of the reasons that we talk about, the second reason, is the fact that a change in concentration, pressure, temperature, all this may have affected our Ecell value. So we just want to see one example, one factor. What happens if I change concentration, and how does that affect my Ecell? So we're going to use an example over here. There are 2 reactions over here, 2 half equations over here. I've also written down all their E0 values. So one of the steps they want to do, very standard, is to consider who is undergoing reduction, who is undergoing oxidation. So let's say these 2 happens in electrochemical cell. Each of them happens in one of the half cells. Mr. William, can you run us through how do we find out who is oxidized, who is reduced?
Sure. You basically look at the E0 values and you decide the one that's more positive is going to favor the reduction process, which is your iodine in this case.
Okay, so I'm put here as E reduced.
And the other guy will have to go through the oxidation process.
Yes. Okay. The next thing to do is obviously to calculate their Ecell. So we have the formula over here that is going to be given by E reduced minus E oxidized. And when this happens, you notice that it is always going to be a positive value. Okay. Now, I'm going to be a bit funky over here. I'm going to start to I'm going to make a change into the system. Okay. So what I'll do first, right, is I decide to go and increase the amount of thiosulfate in the half cell. So I'm going to increase this. So Mr. William, can you run us through what will happen to the Ecell instead?
Sure, right. Just bear in mind, whatever calculations we have done earlier on is under the assumption everything is done under standard conditions, which means the concentration of the ions are 1 mole per dm cube.
Right.
But now you are asking what happens if I were to change the concentration.
That's right.
To increase it. So as you can see, once you increase the amount of thiosulfate, it will go above the reference of 1 mole per dm cube.
Okay.
So by simple Le Chatelet's, they will try to decrease the amount of S2O32 minus.
That's right.
So in this case, equilibrium is going to start to shift backwards, right? So when the equilibrium shifts backwards, what happens to the E0 of that half equation?
So you say that the value is going to drop, but specifically it is going to be the E oxidized value that's going to drop, right?
It's going to get smaller. Okay, so let's apply this to the formula itself, focusing on the oxidation part. Right. So what's going to happen is you're going to minus away a smaller value. Okay, so you do math. You minus away a smaller value, so the end result is that your Ecell is going to be larger than the usual value of 1 mole per dm cube. So this is how concentration can shift the position of equilibrium and therefore affect the Ecell of the overall reaction.
Nice. So it's actually just the same idea as chemical equilibrium. It's all about LCP, right?
Exactly. Okay, so you gave me one question, now it's my turn. Okay, so I'm still pretty upset about the gold, right? Since we don't have luck with gold. Okay, so I'm going to ask you a question, right?
Okay.
What if we throw in silver, right? Silver plus into the solution of I2 to I minus.
Okay.
Can you walk us through what's going to happen?
Let's see whether we get silver specifically, okay? So when we add silver plus, we need to see which part of the whole equation is going to affect. Now, turns out the culprit over here is going to be the iodide. The reason why is because silver plus and iodide, when they mix together, they are going to precipitate out silver iodide, which is going to be what color?
it's going to be yellow.
Oh, yellow.
And it's a solid, right? The Kinetic
Yes.
is a solid. So if it's a solid, you are going to lower the concentration of I minus.
Oh, okay. So that is the main culprit. We are changing concentration, right? And in this case, we're going to decrease the concentration of I minus. And LCP tells us that we are going to counteract this change by increasing the I minus. And that will mean that you're going to favor the forward reaction, right? And what happens to the E value, the E reduced value, Mr. Williams? It's
going to go up.
It's going to spike up, right? It's going to increase. And if I take a look at the equation now, you say that your E reduce is going to increase. And when we talk about this, when we look at the E cell, you realize that the E cell is going to increase as well. Okay? Okay, you give me the second question. Let me throw to you at the last curveball. Okay? So what happens if I decide to add water into the oxidation half cell? Can you tell me what's going to happen?
Okay, so if we were to add water, now we have to ask ourselves, what is adding water going to do to the entire system? Right, so when you add water, you're probably going to increase the volume of the entire system,
That's right.
which means you're going to affect the concentration.
Oh, yes.
All right,
that's
so let's
right.
take a look. You see, concentration is always defined as the number of moles divided by the volume. Right? So now that we have increased the volume by adding water, the end result is you are decreasing the concentration.
Oh,
so
okay.
exactly concentration of who? The answer is concentration of the ions.
Every one of the aqueous species, right?
Correct. So I'm just going to input over here. The stress that we have done is we have decreased the concentration of the ions. Therefore, the response, according to Le Chatelier's, will be the exact opposite. You will now try to increase the concentration of the ions.
That's right.
So we have to go and calculate how many moles of ions are there on each side of the equation. Right? So if you take a look at the left-hand side, you can see that this is considered one ion. Electrons are not ions, by the way. Right? Then on the right-hand side, you will see that there are two ions on the right-hand side. Okay, bear in mind, my objective is to increase the total number of ions, which in this case, where shall I shift to?
I think you should shift forward.
Yes, you should shift forward, right? So you can see I am increasing the amount of ions, I'm shifting the equilibrium forward, which means what happens to the EOX is
It's going to increase, right?
it's going to go up, right? So the same idea, if EOX were to increase, then you're minusing away a larger value, right? And therefore, the E cell is going to get smaller than expected.
Nice. Okay, so some of you might see equations, right, like the one at the bottom over here, where the half equation actually includes the water inside. So can I just make my life a little bit easier? Instead of going through all these ions over here, can I say that if I add in more water, the concentration of water increases, then I just apply LCP?
Oh, you can not.
Oh, okay.
Okay, why not, right? It's because a lot of people think that you can, because water is there, you increase it, you shift
Okay.
the equilibrium. But the problem is, you look at the state symbols, there's a lot of aqueous ions. And aqueous means you're dissolved in a lot of water. So the water is in very, very high concentration. You cannot change the concentration of something that's already in excess.
Right, okay.
So it's the wrong theory to
Okay.
focus on the number of moles of water.
Okay, so I have no choice but to go back to the fundamentals, which is to look at the total number of ions, right?
Yes.
So in this case, for this reaction, you realize there's one ion over here, but there's 14 over here, which means that on the left-hand side, there's a total of 15 ions. But on the right-hand side, you only see 2 of them because that came only from the Cr3+. That's right. So at the end of the day, if you put in more water, you are trying to the LCP will help me to increase the number of ions, which means that it is going to favor the backward reaction to create that 15 ions.
Yep. Okay, now, what if, right, let's make things a little bit more complicated, right? So we have talked about concentration, precipitation, adding of water. Okay, what if we change the temperature? What if we increase the temperature, for example?
But that's not in the syllabus day. But never mind, I'll answer you, okay?
They will sometimes ask.
Oh, they'll ask. Okay, so we're going to think of this as LCP again. That means everything from equilibrium will come in handy. When we talk about increase in temperature, we always have to see whether if the overall reaction is it endothermic or exothermic, right? So if you increase temperature, you obviously want to favor which kind of reaction?
If you increase the temperature, they will lower the temperature, which
Yes.
means they will favor the endothermic reaction.
So you have to see what kind of delta H your reaction will get, and then you just apply the LCP accordingly.
Yeah, so I think the problem with a lot of people is that because delta H is not given,
Yes.
so they just didn't realize that the overall reaction could be endo or exo.
Right.
But once you begin to realize that the reaction could be endo or exo, then obviously changing the temperature is going to have an impact on the position of equilibrium.
Nice. So everything from chemical equilibrium will just come in handy here.
Okay, one of the key things that I think we have to master is the ability to write equations on your own. So if you look at your notes, there's a portion of fuel cell. Now, although there's a self-reading portion, but I think the skills behind this is quite important. So maybe let's go through this with the class.
Yes.
Now, typically in exams, you'll be given certain setup. It may or may not be a fuel cell. Your job is to be able to be comfortably coming up with the equations over here. Why is this the anode, for example? Why is this the cathode? And why are the equations done this way? It's not about memorizing, right? It is about this particular concept, which I always like to phrase it as we fit the environment, right? So you have to look at the environment and you find equations that perfectly fits into the environment. Okay, so for example, if we look at the left-hand side, right, let's say we have no idea this is anode, no idea this is cathode. We are going to derive the process. So Mr. Leong, as we look at the left-hand side, what do you think is present inside the environment?
Okay, so the diagram tells me that you are feeding in hydrogen gas, and when Mr. Williams says about the environment, we are talking about the electrolyte. So in this case, the electrolyte is going to be hot aqueous KOH, which indicates that this is going to be done in the alkaline environment.
All right, so the environment has a combination of hydrogen as well as OH minus. So I'm just going to write down here, it is H2 as well as OH minus, right? And at the same time, we look at the right-hand side, walk us through what is present.
Okay, so they're feeding in oxygen gas, so that's the focus. And of course, once again, pay attention to the environment of the electrolyte. It is going to be alkaline medium as well. So we're going to see OH minus and O2.
Okay, so the first thing that we have done is we have located what are the species inside the environment. Okay, the next thing we're going to do is we're going to browse through the data booklet together. Okay, so let's do it. We go to the data booklet. Now, as you glance through the data booklet, it doesn't matter whether it's on the left-hand side or the right-hand side, it doesn't matter. All we want is to fit the environment. So you're going to glance through the entire data booklet, find the equation that has H2 and OH minus, right? So as you glance through the entire thing, right, you do realize over here, the one with negative 0.83, it falls into what we're looking for, H2 and OH minus, right? You look carefully, there's no other equation that actually does this. Whereas on the other side, what do we have? We have O2 as well as OH minus, right? So again, we're going to find this equation, and you will see that the one with 0.40 is what we're looking for, O2 and OH minus. So this is what we mean by you fit the environment. Just find things that's inside the data booklet. But that's a problem. Now the problem is both equations are written as reduction,
right? Which
cannot be the case, right?
Yes.
So what do we do next?
We once again have to determine who is undergoing reduction oxidation by looking at the E0 values, right? This is a electrochemical cell, so the method has always been the same. The one with the larger E0 value will always be the one undergoing reduction. So in this case, we saw that the plus 0.40 is larger, so your oxygen is getting reduced, and on the other hand, your reduction equation is where your hydrogen is going to get your hydrogen is going to get oxidized.
Okay, so once we have this thought process in mind, knowing that this is going to go forward, the reduction process, and this is going to go backwards, the oxidation process, this is where we're going to return back to our notes, right? And you re-look at the equation that's given, right? Do notice this is written as the oxidation process, and this is written as the reduction process, all right? So only when you have this being sorted out, then you can label this is going to be the anode, where oxidation is taking place, and anode is a negative terminal. Then on the other side, it will be reduction, which is cathode, and this will be the plus terminal. So just bear in mind this fits the environment to decide who gets oxidized, who gets reduced, and then you just do whatever that we have been teaching you all this time.
Yes.
But that's a shortcut, right?
Yes. So what happens if the question didn't really give you the environment? So usually the question would somewhat be kind enough to give you the starting point and the ending point. It means the reactants and the products. So I think based on that, you just need to fit and find out which of the reactants is undergoing oxidation, which one's undergoing reduction. So for example, in this question, I could have said that, hey, oxygen can no longer be further oxidized. It must mean that oxygen definitely has to be reduced, right? So what I do is I can go back to the data booklet and see the oxygen, go and check out the oxygen that's on the left-hand side of the equations. Conversely, if you want to take a look at hydrogen, you say obviously hydrogen is going to get reduced. So what you can do is you can just look at the data booklet, make sure that the hydrogen is on the right-hand side of the equation, right? So that will be another method to help us to determine who is undergoing oxidation and reduction.
Hydrogen is getting oxidized, right?
Hydrogen is getting oxidized, yes.
Yeah, so these are two different ways to look at it. Either you fit the environment, or if you are clear who gets oxidized, who gets reduced, then just write the equations according to the data booklet.
Okay, so that's it for Electrochem. We will see you in class. Bye.